Hi all. I see Rohi is joining in. So is Saransh. Let's give it a minute then. Hello everyone. I hope you can hear me. Give me 2 minutes. I'm just trying to run my Jupyter notebook so that we can start from where we left off yesterday. So let me just share my screen and then we can go ahead. So where is that button? Yeah. Give me 1 minute. Yeah, we got it now. Hope you can see my screen.
Yes.
Yeah. Okay. Okay. So until yesterday, what we have looked into is as simple as we have looked into the fact that we can clearly see the PDF and the CDF. Now, looking at the PDF and the CDF, we get to know some very essential information. So let's just quickly recap what we saw until yesterday, and then most probably we are going to continue from where we had left off. Yeah, and then we'll see how we can try to do more of the visualization things. We will see one very important visualization uh, that helps with respect to statistics. We have already seen that earlier briefly when we were doing sessions onto Matplotlib, but we will be looking into that right now as well so that we get some very good idea now. So we will look into two kinds of visualizations to look into the 5 point or 7 point statistics that we have already seen. So that's going to cover a lot of basics, and then we will look into multivariate probability density, because as of now we have just seen the univariate uh, probability density. Here the PDF functions that we have seen in our charts, they are all related to a single variable at a certain point in time as compared to another variable, right? So we will quickly touch base into multivariate one as well. Now, before we do that, let's quickly see what is happening over here. So what we concluded yesterday is that this blue line is the PDF, obviously, and the orange line is the CDF. Now, when I talk about the orange line, the advantage which I see with the orange line that I can see over here is that the orange line, obviously being cumulative, is actually one thing, but then the other thing that I see over here is over a period of its growth, it's actually taking a shape, and that shape, as I have already tried to define yesterday, it's a logarithmic shape. Why is that logarithmic shape? Is because logarithm exists within the same range as the probability range, and then a logarithmic shape on the scale of a graph like this one, the one that we are showing over here, is a very smooth kind of a graph that starts from 0, has a slant over, and then it goes over to 1. Now this gives us a very good opportunity, as we saw yesterday. Let's just quickly recap what we saw. Is that if I'm going to draw a line which is something like this, let's say I'm just going to draw a random line over here. Okay, you can safely ignore this PDF right now. We are only looking at the CDF. Okay, so this is the CDF, this is the PDF. We are going to look at the CDF right now. We'll only concentrate at the CDF. If I am, able to draw a line like this, then I can clearly use this, also known as a decision boundary. And using this decision boundary, I can clearly say that this number here, or the x-axis over here, in this case, I believe this was petal length. I'll have to cross check once. I think as per the code, this was actually petal length, and this PDF and CDF actually refers to setosa flower, right? So for setosa flower, it is quite clear that I can create a decision boundary using the petal length variable. So petal length variable plays a very important role. But then I have already seen that when I have seen the correlation matrix, right, or the correlation coefficient, then what is the kind of advantage that the CDF is actually giving me? The CDF is not only a visual representation that I have over here, it's also telling me how good probabilistically my data is actually divided. Give me 1 minute. Yeah, I'm back now. So it also gives us a very good probabilistic view. Now here you can see it's kind of a straight line. And here we are considering petal length for the second case. Second case is actually, let me see. Yeah, that is species equal to 1. So this should be Virginica. I hope that should be it. Let me just quickly check what was the second flower. Yeah, the second flower was actually versicolor. So in the second block of code, I'm taking petal length with species value equal to 1, right? So the first block was referring to setosa. Second block will be a versicolor. So versicolor in this case is not having kind of a logarithmic graph. So it will become very difficult for me to create a decision boundary. We will look more into a decision boundary at a later stage. But the reason why I'm stressing on this point right now, or at this stage, is that when we are doing such kind of analysis, let that be univariate or bivariate, we are applying a lot of concepts of statistics and probability that we have learned. That's the reason why we are trying to revise all those concepts that we have learned basis the code that we are writing, right? But the advantage here is not only to do statistics, it's also to gain something out of it. And what we are gaining here is that if we can clearly see if there is any decision boundary, then it clearly helps us understand what kind of, let's say, approach or let's say methodology are we going to use when we are going to do the actual modeling part of things, right? So when we go into actual modeling, this kind of background information is really going to help us, right? Also, as I have already told you, the best practice is always that we write down whatever findings we have, and then basis those findings at later stage. So we can write down the findings at the uh, 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 inside the notebook itself, right? And inside the Jupyter notebook, if I write down my findings, then at a later stage, I should be able to just a moment. I should be able to refer to those outcomes, and then basis those outcomes, I should be able to take a decision as to what kind of a modeling that I'm going to use, or what kind of things that I'm going to do as part of the modeling. So that is the basic reason why we have done all these things over here. It's not only to revise the statistical concepts, but also to get to a point where we can understand what we are actually going to do when we do the modeling, right? Now enough said, let's move ahead with what we were actually supposed to do today. So what we are going to do today is again something related to statistics only, but more into a visual format. Okay, so when we look into statistics but more into visual format, there are two kinds of plots that I frequently use, that statisticians also frequently use, and that gives a very good kind of outcome, uh, and it helps us understand the data very well. So before I do that, let me just finish this part of the analysis with the comments which I have over here. So I'll just make this a markdown cell, and I'm going to write basis the CDF as populated from the PDF using petal length as the defining feature for each species of iris flower. We find that in case of setosa flower, we have a somewhat natural logarithmic type or logarithmic like graph of CDF, which means petal length can prove useful, very useful to create later on during modeling phase the decision boundary for identifying the Setosa species. Unfortunately, in the rest of the two species, we do not find such case. Okay, which is fine. I mean, whatever our understanding or whatever our finding is, we are just going to write it down. We're not going to conclude anything. Right. Now, what we are going to do is let's look at those two quick and very easy ways of the visualization that I was talking about. The first thing that we look into is a box plot. A box plot is something we have already looked into, right? But box plot is something which is also a very, very good and a very important statistical kind of a measure, which gives you the visual concept or the visual way of looking at let's say the concept of mean, median, mode, median, percentile, quantile, okay, and then it also gives you the interquartile range kind of an idea. Okay, so what we are going to do is that we are going to use a function. Let's plot the box plot representation of the data. So what we are going to do, let me make it simple by creating box plots basis each and every feature. Okay, each and every column, which is petal length, petal width, sepal length, sepal width, and then I will look into the species information. So to do that, what I'm going to do, SNS dot box plot. SNS, if you remember, is my Seaborn library. Here, what I'm going to define, what is going to be the value of X, what is going to be the value of Y, and what data am I going to make use of. Okay, so data, obviously, I'm going to keep the value to the data variable equal to the data frame. Y, let's say, is going to be petal length. Okay, and then let's say X is going to be species. Okay, there is a specific reason why I'm doing this, why I'm putting the feature on the y-axis, and my most interesting variable. I'm not going to give it a name. It's also called a target variable, but this is not the right time to give it a name because we're simply exploring the data. We don't know what kind of target we have, right? So we just have some vague questions which we have already written down earlier in this notebook, which we are trying to answer. So at later stage, in certain circumstance, we are going to call this species column as a target variable, but we may choose not to call it as well. It's not a mandate. It is driven by the question that we are asking, is that we are going to call some of the columns as features or independent variables, and some of the columns, or especially one of the columns, as a dependent variable, otherwise known as the target, right? So here, what essentially this line of code is going to do, and let me also add this pld.show command, is that it's going to give me a very good representation of the box plots of all the three species. Note that because I've already converted the data, right? So I've masked the data in form of 0, 1, and 2 using the label encoder. That's why I don't see the name of the species, which is fine because I know what those names are, right? 0 refers to Setosa. Species 1 that refers to, I believe it refers to versicolor, and 3 refers to Virginica, right? Now, what advantage does this graph give us? It clearly tells us if there are any outliers. The first thing we notice are the outliers. Okay, the first thing that we notice are the outliers. If you're not able to see that in the graph, you can increase the size of the graph, and that you can do using something like this. Let me just use a function called plt.figure, and inside this I'm going to say fig size is equal to, within the brackets, let's say 10 comma 10. If I print this now, you see the graph has actually become bigger, which is not a very bad thing, even if it is getting expanded out of my screen of this Chrome window. It is all fine because it clearly shows me if there are any outliers. So the first thing I notice, this green bar, this represents to species number 2. Species number 2 is what? Species number 2 is going to be Virginica, right? So 0, 1, and 2, these are the three categories. So Virginica is going to be 2. So in case of Virginica, base is the petal length, right? This is the y-axis that I've taken. Base is the petal length. There are no outliers in the data. However, base is the petal length for species 0 and species 1. We do have some outliers. Okay. Now, what is the reason why again we are looking into outliers here? We have already talked about outliers, right? Why we are looking into outliers is because at later stage when we start doing inferential statistics or hypothesis testing, further we are going to move on to modeling. These cases are going to hamper us. So we need to see if there are many cases. The advantage of using this SNS.boxplot is, although sometimes it is a bit hard to visualize, so what people usually do is, let's say here I have 3 species, right? So maybe I'm going to plot one species first and then the next species. So rather than taking this one, this iris data set, you already know I have another data set, right, which is iris underscore setosa, which I had already created in the last step. So why not use this one and try to plot that? So in that case, it's only going to plot the case of the setosa flower with respect to the petal length. And what the advantage it gives is that this plotting kind of a mechanism using Seaborn gives a very clear idea of the count of the outliers which you have. So here you can clearly count the number of outliers which are there, right? And you can also see how much distant they are from the whiskers, okay, or from the borders of the box plot. So this gives you a very good idea that if, let's say, how many data points are there for each and every species, we know there are 50 and there are only 3 outliers, which means this data set, even if there are outliers in the data, it is okay. You don't need to do any kind of pre-processing to handle the outliers. Okay, you don't need to do anything. This is a very good intuition that you get before you do any kind of inferential statistics, because you need to know if there are any confounding variables or if there are any effects which can cause biasness in your inference or in the model which you are going to create at later stage. So this is really important to find out. The second thing, again and again, we are trying to again go back to the same old kind of a question: is there any marginality, or is there any clear-cut kind of a demarcation which is created by the petal? And the answer is yes. At least for the setosa flower, there's a clear demarcation with respect to the rest of the flowers. While we do see there are certain overlaps between this orange box and the green box, but hey, here the orange box is ending here and the green box is over here, so I don't see any practical overlap here. Then why am I saying that there is an overlap? The overlap is because of the whisker, and the whiskers, the endpoints, they represent the range of the value. Okay, so these upper bounds and lower bounds are actually the range of the values which is contained for that specific species related to that specific feature, and that gives us a very good idea about the balance of the data as well. For example, if you see over here, the max is here, the min is here. Visually you can clearly see this data is not really properly balanced. None of them are. Okay, but if you look at setosa, it is almost quite well balanced. If you look at the, let's say, versicolor, it's not really bad. The third one is a bit extended or a bit exposed into at the lower side, into the lower side. But that's, let's see how it is going to affect. So as of now, we clearly see there is some kind of a pull for this green color towards the bottom. At a later stage, we'll come to know why this pull and push is really useful, because if you have this range of the data pulling towards the minimum as opposed to the maximum, then you will have an imbalance problem within the data. And you may need to use some kind of techniques later on when you do, especially when you do modeling, to get rid of the imbalance problem. But here, as we have already said, we are just taking this data for an example because it is a toy data, right? So you may not find such kind of problem, but it's good to look at this. Now we have already looked into one. Okay, we have already looked into one of the box plots. Why not look into all of them using a quick for loop? Okay, can we write a quick for loop to look into all of the variables at once? I believe we can. So let's see how we can do that. So for each column in iris dot columns, okay, I'm going to use a quick for loop, and what I'm going to do is that I'm going to do something like this. So I'm going to say if each column is not equal to, is that the right sign? Let me, I think this was the right sign, but let me try. If it is not even species, it is not equal to species. Okay. If the column is not equal to species, then this is what I'm going to do. I'm just going to tab this so that it comes in the right place. And Y, I'm going to give each column, and then I'm going to do a plot. So let's see what this results into. So the first one results into sepal length, second one results into sepal width, third one results into petal width, petal length, fourth one results into petal width. Okay, so this gives a very nice idea. And then let me just do one thing. Let me just hide this part so that I get, at least for this demonstration purpose, I get all the graphs in a very nice order. Now you can clearly see sepal length is also very good in bifurcating, but there is still some kind of an overlap. Here we see a very good kind of an analysis, is that basis the sepal width there are some outliers, but basis the sepal length there is only one outlier in the entire data set. Okay, so sepal length and sepal length I believe is the only feature basis which we have the least number of outliers in the data, right? The second thing is you can clearly see basis the sepal width. Okay, the mean sepal width or the average sepal width, this middle line is actually representing you the mean. Okay, so the average value represented by the middle line in these box plots clearly tells you that the average of the sepal width for setosa flower is actually more than that of the rest of the two. So you can clearly create an order, and that gives you a very good kind of intuition as to what kind of a range in which your value falls into. Okay, but there is one more thing that you can clearly see over here. I really like this plot. This guy over here, I really like him because it is like really well balanced in the middle. Right, if you look at the range top and bottom, it's really well balanced here, right? Then we have the petal length, which we have already seen earlier, and then the petal width. So clearly here also you can see petal length and petal width, although they are incurring some outliers when it comes to setosa flower, they are a clear demarcation factor uh, between the setosa species as opposed to the rest of the uh, species of the flowers. So this is one kind of a visualization. It's really going to come very handy. The other kind of visualization is something I will simply tell you. Okay, but I'm not going to explain that to you. Okay, this is going to be your homework. I'm simply going to explain you something. Okay, and then you have to explain. Okay, rest you will have to find out. I am just going to tell you something funny, and then the rest you will have to figure out, and you have to tell me tomorrow what you have found out. Okay, instead of doing this plotting, I'll simply take this code. Okay, and I'm going to create another set of code. Okay, let's now, so I'll just change the text here. Let's now look into all of the features using a quick for loop and visualize the data using a very interesting technique called violin plots. Okay, so let's see what violin plot means. Okay, just the function name is going to change. violin, violin is the spelling. Okay, violin we already know it is a musical instrument, right? And I'm just going to mention a size over here. So let's say I'm going to mention a size of 6. Okay, why I have mentioned the size is related to the comic feature that I'm going to tell you. So if I press shift enter now, I can see there are certain plots which are here now. Okay, now the only thing I'm going to tell about them is that if you look at them carefully, these look like some kind of seaweeds, right? So some kind of underwater fish like animals, right? Which we may have seen into television. Now the only thing that I'm going to tell you is that more the breadth of the belly of each and every insect or animal that you are seeing in the violin plot, the more hungry they are, okay, or the more flabby they are. Okay, so here we see there is a nice balance of each and every bellies. Okay, I will call the middle part as a belly, but here you can see one person's belly is very fat, Okay, this guy is very short in height and his belly is really fat, while the others look in quite good shape. So I would like you to figure out what this is going on over here. I'm not going to tell you what is happening here, okay, but I can only give you a hint that this belly like shape that you are seeing over here represents a distribution. Okay, I'm not going to tell you what the distribution is. You have to figure that out. You tell me what you find out from the internet by tomorrow. If you have any doubts, we are going to clarify that. Okay, so this is also a very interesting. If you are able to find out the answer of this question as to why this is a very interesting plot to look into, and how does it help you understand the variation or variability of the data per each and every feature, then you will start appreciating the fact that Violin plots are really useful in understanding the overall distribution, or to compare the distribution of each and every uh, values of a categorical variable as opposed to a numerical variable. Okay, that is exactly what we are trying to do over here, but I'll not tell you more. Okay, I hope that's fine. Then let's move ahead with the next set of activities that we need to do. If there is any question here, please do let me know. Any questions from anyone? Any questions from you, Rohi? Any questions from you, Sarangs?
No, Mobile, clear for me.
Okay, okay.
No.
Okay, sure. So let's quickly look into something else as well, and then I'm going to also give you one more exercise for today, something that you can try out. I'm going to give you a link of a certain, let's say, you can call it a data set, because it's kind of it was part of a free competition, the website called Kaggle. We are almost at the end of this data analysis kind of thing, so we are only left out with the hypothesis testing or the statistical tests kind of things, right? So once we are done with that, we will be complete. So that's why I would like to give you the data set or the link to the data set, and maybe what you can do, you can try and find out the data itself. You can try to download it, and then what you can do is that you can try to perform similar kind of the analysis that we have already done in this IPython notebook, right? So essentially you can take a reference. This IPython notebook, the one that I'm sharing on my screen, is already updated into our LMS portal. Okay, so you can get the IPython notebook from there. Okay, and then you can try to uh, look into the data in a very similar way in which we were looking into. Okay, next is we are going to look into distribution. So let's see if we have time today, and then we will see how it goes. But before we look into distributions, let's do a quick plotting technique with something that I'm not going to explain you right now, but we will look at a quick plotting technique, which is going to look at multivariate probability density. Okay, so as of now, we have only seen single variables. You see, I've considered species as very important here, and then I've tried to compare whatever distributions or variations of data I have with species, as opposed to each and every singular variable. I have not tried to combine multiple variable here and try to look at something. If you want to combine multiple variable, it will be good to actually use those uh, data frames. Let me just quickly go back. When we calculated the CDF, right, we use these small kind of, let's say, data frames, which are like 50 rows each, right? So each and every species had a single data frame. So this is exactly the one that I'm going to reuse here, and I'm going to try and create probability density plots for a multivariate analysis. So rather than using one variable, now I'm going to combine two variables. Okay, earlier I was using only one, now I'm going to combine two. Okay, here in this case, to make it simple, I'm not going to draw the CDF, because CDF is going to make things really complicated over here. I'll only focus on the PDF first, and then we'll see how we can get ahead. To do this, again, in Seaborn, we have a feature called joint plot. Why is it called joint plot? Is because we are joining. Okay, we're trying to join the distribution of one feature with respect to the other feature, and then we are going to compare it and we are going to limit ourselves to look into only one kind of a categorical variable. In this case, let's say we are going to take each and every species, and then we are going to look into it. Okay, why not? I'll do one thing then. What I'm going to do is that I'm going to plot the joint plot first of combination of two variables, and then we see if we can create any loop, or maybe I will be leaving that up to you to beautify this code and try to make it within a loop so that you can try out all the combinations. I'm going to try just one of the combinations and let's see how it goes. So here also, in this case, in case of joint plot, also similar to the plots that we have just seen, we have the variables x, and then we have y, and then I have the variable data, which is going to where I'm going to pass my, let's say, the data frame. And then I have to put some kind of a variable called kind. In this kind, I'm going to put a value, and I'm not going to explain that to you right now. Okay, I would strongly recommend you can look into Google as to what is KDE, but please don't get too serious about it right now. These are one of those points which I have deliberately not explained when we were looking into theoretical aspects, because you wouldn't have understood what is KDE. It is actually a process to create the probability density function. That's it. KDE is just a process to create the probability density function. You wouldn't understand that unless and until I do some practicals and I explain that to you. So we will do that. Okay, we will do that quickly in the next class maybe, but this is not the right time to discuss about KDE, because discussing KDE theoretically is only going to confuse you. That's why I'm going to skip this part right now. But it is just to let you know that KDE is just another mathematical process by means of which, as we have already seen briefly, we have histograms of data, we had bins, we had histograms, and by joining the tips or the edges of the bins, bin edges, what we call them, we were able to create the probability density function, where on the x-axis we had the actual values of the random variable, and on y-axis we had the probability value ranging between 0 to 1. Simple, right? Now in this case, in this joint plot, what did we say? We are going to do a multivariate analysis. So let me take two variables here. First one, I'll take petal length, and then I'm going to take, let's say, petal width. Okay, in the data, let's say I'm going to limit my analysis. Let's not try to look into all of it, or maybe we can try to look at all of it as a start as well. So let's try to look at all of it. Okay, although this is not going to be very definite, later on we're going to change this data variable value to the specific data frames which we have, right? If I do this, it's going to take some time. Okay, depending on what is the size of the data, it's going to take some time. But now we get a very, very interesting plot. So let me just zoom this out so that you can clearly see it on the screen. Let me explain what is happening over here. There are two things which is happening here. Okay, and these are very, very important things to remember. Okay, very important things to remember. The first thing to remember here is we are having two kinds of plots. One is on the top or on the sideways. So these are kind of plots which are drawn over the borders, right? So you can see there are four borders of the entire diagram, right? Now here is the x-axis, here is the y-axis. We have the values here. Okay, clearly these are not the probability values. Okay, these are the actual values. Please don't get any confusion. These are the actual values of the petal length. So this one is the petal length. This one is the petal width. That's exactly what I've used, right? X is equal to petal length, Y is equal to petal width. Okay, data is entire iris. And here I'm doing a plotting where this is actually the multivariate probability distribution. Okay, if you look at the PDF of only the petal length, you will come to know it is just this. Okay, so this is nothing but the PDF. Clearly this is the PDF of this. So if you're looking at the PDF graph, which is this one, you need to go downstairs, okay, in the building, and go downstairs in the building and look for the person to whom this PDF actually belongs to. That's the x-axis. Right, so anything here on the horizontal scale is actually representing the PDF of the value which you have taken in the x-axis. In this case, that is petal length. Similarly, obviously, this PDF belongs to petal width. Okay, you can compare that. If you want, you can go back to the diagrams which we have created earlier, and you can try to compare. They are exactly the same. But then why did we draw this? If you have already seen the PDF, then this is kind of a time waste, right? We have drawn this because of this. This joint plot has resulted into something at the middle portion, and this middle portion is really very important. This middle portion, okay, is otherwise known as a contour plot. You can read about this on the internet, but I'm going to explain this to you in a very different way. How do you infer this is something like this. How we are going to infer this is something like this. Let me draw a diagram. Okay, let me take a different kind of a color, and I'm going to draw a very bad diagram. It doesn't need to be a very good diagram. Okay, I'm just trying to draw a very good uh, scenery here. I'm just trying to draw. This is like a mountain, right? And there are trees. Okay, so I have a mountain and I have some trees at the bottom. I will have some trees on the mountain, on the slopes as well, right? You just have to imagine that there are some trees. Although I'm not saying that this is like a jungle kind of a scenario. It might well be, but just to simplify, and you will come to know why I'm trying to simplify the setup. This is just a mountain which I have, and I'm trying to get down of that mountain. Okay, so let's say this is me. I'm standing on the top of the mountain. Somebody has dropped me on the top of the mountain, right? And now I am given a task that I have to come down. Okay, how do I come down? I have a lot of ways to come down, right? Because this mountain that you see over here has a lot of sides. Okay, I can come from this side, I can come from this part, I can come from this part, I can come from this part. Essentially, there is a 360-degree view that I have. I've only drawn the 180-degree view. This view that you can see over here is the 180-degree view, right? You also have a backside of this thing, right? So that is also the rest 180 degrees. So you have 180 degree here, 180 degree there. You have a full 360-degree view. Now you have many different places from where you can get down. So I have a plethora of options. That is the reason why now I have a question mark. From which way do I come down? Then again, I also have a lot of problems here. You see, there are trees. If I come down from a certain road, and let's say there is a tree over here, I will get blocked. I may have to change the route. So the route may not be a very kind of, let's say, it will not be a very simple life for me that I start from here and I simply take a straight route and I come down to the bottom. In which case I could have used a rope as well, right? I could have slightly slanted down, and I could have used kind of a support with a rope, and I could have come down. But I may not be able to do that because I can clearly see in this context there are trees, right? Then what exactly am I going to do? My task, the answer to this question is to figure out, and this is actually a question. This diagram over here is the same question. This diagram over here is the same question. How do we reach the bottom of the mountain optimally? Okay. In the mathematics world, in the computer science world, this is known as an optimization problem. Also, it is a type of an optimization problem which is known as the minimization problem. What I'm trying to do is I'm trying to minimize the risks or the time that any human being, in this case, that is me, okay, how much time or how much less time and less complexity can be spent for a human being to come down. Okay, this is just like the time and space complexity which we see into programming as well, right? We often choose to ignore that, but it is our duty as a programmer that we must choose the right data structures and algorithms and the combinations of these two, so that we can actually figure out the best possible way to execute a certain program or to write it, in which case we will be reaching the outcome faster. So let's say I've written a very poor code and it has a lot of for loops and while loops and so on. It might be running for half an hour and then I get an output. The same thing is written by, let's say, Sarangs, and he is able to get that output within 2 minutes, which means he has optimized his code. He has made his code performance friendly. In the same way, the same question stands over here as well, right? For me, for this human being to come down from the top of the hill to the bottom of the hill, I have the same problem. I have a minimization or minimization optimization problem. Okay, I have to come down to the bottom of the tree, and this bottom of the tree in this diagram, this contour plot, is represented by this dark place. Okay, this dark place is also known as local minima. You have to come to this local minima from wherever you want to start. So let's say I want to start from this part of the top of the hill. Okay, I have to come here. or I have to start from this part of the hill, I have to come here. I have to start from this part of the hill, I want to come here. Any place you start, you have to figure out a way. Let's say a way. It is just like a puzzle which you play, to find the shortest route towards the treasure. It's kind of a treasure hunt kind of a puzzle, where you are coming down towards the treasure, which is the bottom of the uh, 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 the pyramid, or the structure on top of which you are here, and then you have to come down to the bottom using the most optimal way, so that you can reach there as fast as possible and as less complex as possible should be the way that they have followed. Okay, this is the advantage of looking at a contour plot. Okay, the contour plot simply tells you how easy or how difficult it will be to come down. Now, why are we discussing so much about this? Let's continue tomorrow because we don't have time. But again, a question for me before we leave. What do you think is the difference between this part of the contour plot and this part of the contour plot? Consider these two as two different mountains. Let's say Rohi is standing here and Saransh is standing here. I would like you to answer whose life will be easier, who will be reaching the bottom of the mountain very easily. Okay, I'll leave that question for tomorrow. Let's make it a close here. We don't have time now. I'll be sharing the notebook, and I'll also share the data set which I was actually talking about, and then you can do some practice. Okay, thank you so much. Thank you. Good night.
Thank you, Amit.
Good
Thank
night.